Hello, welcome to our last introductory video for this unit on rotational motion. We're going to be focusing today on angular momentum, which I'll get to in a moment. But before I do, I want to introduce a topic that I haven't introduced yet, and that is this equation. The net torque is the moment of inertia times the angular acceleration. Let me refresh your memory from a couple chapters ago. Hopefully this looks really familiar. Newton's second law. This equation is often referred to as the rotational version of Newton's second law because you can see mass, moment of inertia is in mass, or has mass in it, and this is linear acceleration, rotational acceleration. This is an equation which we will use occasionally, and that says that the power is equal to the torque multiplied by the angular speed. Okay, so now on to angular momentum. Angular momentum is the moment of inertia multiplied by the angular speed. So far in physics, we've encountered two things that are conserved. The first was energy conservation, provided there weren't any non-conservative forces like friction present. And the second was linear momentum was conserved. Well, now we're looking at rotational momentum. That, if there isn't an outside net torque, so we're not adding rotational energy or removing rotational energy from a system. If there's no net torque, no net twisting motion being put on the system, then the angular momentum is conserved, where angular momentum is defined as moment of inertia times angular speed. Now you've probably seen this at play many times before. A common example that we often use is an ice skater that maybe has a leg out and their arms out and they're spinning slowly, and then they pull their arms and legs in, and what happens? They go faster, right? And that's because their angular momentum has to be conserved. And so initially, they have their arms out and maybe even a leg out. They have a moment of inertia that is large, and they're going a particular speed. And when they pull their mass towards their core, they're taking that mass and they're bringing the R in very close to the axis of rotation. So the moment of inertia is going down, and that causes the angular speed to go up. Great, let's work some problems now.